Alrighty, welcome everyone. It is August 15th, 2024, and today we're going to continue our discussion of linear regression, but we're going to do so in maybe a little bit of a unique way. We're going to take a slight break from the minutiae of linear regression. We're going to talk about a separate but complementary algorithm called gradient descent. Now, why are we doing this today? Why are we taking this pause right now? Well, gradient descent is probably the most important algorithm in all of machine learning. It is really how machines learn, and in particular, it's how neural networks learn, which is far and away the most powerful category of machine learning algorithms that we have today. And it just so happens that as we're using linear regression, particularly simple linear regression, which remember just has two parameters, just the slope and the intercept parameters, in order to define that line of best fit to our cloud of data points, well, it's really easy and I guess possible for us to make visualizations, make graphs, make an interactive tool and lessons about how gradient descent does its work when we only have two parameters. Once we have more than two parameters, 3, 4, 5, thousands, millions, billions, as some models have today, the potential for visualizing the entirety of the model's parameters goes out the window in a hurry. Really, any more than two, and you've got some problems. So I think it's so important in building our intuition for gradient descent and for this overall picture of how machine learning works to take this opportunity when we're working with such a model that is so simple, so approachable, to use gradient descent to fit linear regression to data. Now, last week we talked about simple linear regression in the terms of, we talked about, let's just review. I'll scroll down here. I've got some of the things we talked about last week repeated here. And by the way, we're having this lesson here on Thursday because I had to push back our typical Tuesday time. Next week, we'll be back at our regular Tuesday, 8 p.m. Eastern time schedule. So you can look forward to that. But last week, we talked about error metrics, right? How do we quantify how close our prediction is to the true value and do that across all of the different predictions that our model can make? And with linear regression, our line of best fit represents all of the predictions our model could make. And so if we look at the distance between that line and the individual data points, well, then that's a way of putting a number on how good or bad the predictions are. But we want one single number that can kind of quantify that for the whole model. And the distances between these data points, well, that's a lot of different numbers. How do we take all those numbers and put them into one single metric? Well, we can average them, average the absolute distances, get mean absolute error. We can average the squared distances, the squared deviations, the squared residuals, right? All those are kind of synonyms for each other. And if we do that, we'll get mean squared error. And if we take the square root of the mean squared error, we get root mean squared error. And those are error metrics, sometimes also called loss metrics or cost metrics. And they're going to play a big role in what we talk about today with gradient descent. We also talked about last week how linear regression works to minimize the sum of the squared residuals and how it finds the very best slope and intercept parameters for our model, right? Calculates this line of best fit. And that's all great. The thing about linear regression is because we have this nice equation that describes this line, basically, we can solve directly with mathematics for the slope and the intercept that goes through the middle of those data points as well as it possibly can. However, we don't have to do it that way. And in fact, there are many machine learning models where you can't simply solve directly for the best parameters. You have to estimate them, or you have to discover them in one way or another. And this is what gradient descent is really all about. How can we hone in and narrow down what the absolute best parameters for our model can be when we can't solve for them directly? This is a little bit of a unique case because we could solve for them directly, but due to the simplicity of this model, we're going to be able to really hopefully wrap our heads around how exactly gradient descent helps us find the best parameters. Okay. If you were here, I don't know, a couple of months ago when we had our very first machine learning workshop, I shared this graphic here. And in fact, I accidentally deleted the slide and the slideshow that I had this on. So this is a screenshot of that YouTube video. But we talked about a bread making machine and how bread making machines are different than machine learning machines because a bread making machine has to be built specifically for making bread. Right? It's meant to take in very specific inputs, do very specific things to them, and spit out, hopefully, a nice baked loaf of bread output. We also talked about how machine learning models are unique in that they're not programmed to do any one thing. Rather, we give them good inputs, we give them good data, and we do expect quality outputs. But what happens in the middle, what happens in the internals of the machine, we're kind of hands-off about. We let the machine figure that out on its own, right? And so we talked about this iterative pattern of giving the machine inputs, letting it run for a while, seeing what it spits out, right? And we talked about maybe the first time it runs, it spits out a black lump of charred, something barely recognizable. And we say, no, machine, bad. That's not what we want. We want this nice loaf of bread. And we show it the correct output. And it goes and it slightly tweaks its internals somehow, however it chooses to do it, and runs again and puts out another output, which maybe is a hair closer to what a good loaf of bread should look like, right? And if that process gets repeated enough times, even if our machine's kind of doing this random walk through, possible modifications it could make to the bread inside the machine, like eventually it's going to stumble upon a combination of techniques and practices that will lead to some decent looking bread. And we talked about how that's maybe a better analogy for machine learning than a lot of the talk about AI today. Well, what I'm going to show you today, gradient descent, is really this bread machine. Gradient descent is one of the most efficient and most practical methods that we have for getting machine learning machines to learn on their own, to in a supervised learning fashion, show them that good loaf of bread, show them what the true prediction should have been, and allow them to see how far off they were from that prediction when they generate an output. But we're going to see what happens on the inside of the machine today, and in that iterative fashion, be able to make better and better and better and better and better and better predictions until we converge upon the best possible output we could possibly make. Okay, so I don't know if you remember that. If this analogy is not making any sense to you, go back and watch that very first machine learning workshop video. You can access them at temzee.com/machine-learning-workshop. All of our past workshop videos are there. All right. But before we do that, before we start writing code here, before we start going over examples, let me share with you the starter notebook for today, which you can use to follow along if you want to code along with me, which I strongly recommend. Oh, and that is the starter notebook. All right, and we also have the notebook that we're going to use here live, that I'm going to be coding in. These are also in the description below the video, but they're in the chat as well now. Okay. I'm going to close this other tab because we're not going to be using it. And let's get into this. So what is gradient descent? Well, it's an optimization algorithm for predictive models. We'll talk more about what that means. And so much of my understanding, and I think your understanding of gradient descent, is going to revolve around something called your concept of a loss function, also called a cost function, also called an error function, also called an objective function. There's lots of names for it. Any function that we try to maximize or minimize and do quote unquote optimization around is sometimes called an objective function. But in the context of machine learning, you're going to hear this referred to as a loss function or a cost function. And a cost function describes the quality of our model's predictions given all the different possible parameters that my model could take on. And we actually built a loss function last time. I'm going to remind you of this, right? We had our our data set. And in fact, we did it a little bit differently last time. We sampled this data set, so we just used 7 data points. I'm going to do the same thing today, but I'm going to use all the data points. Okay, so I'm going to run some of the cells that are already here, load our data set. Here's our scatter plot. Our simple linear regression model that's being done with scikit-learn here is solving directly for the slope and the intercept values that are the best. Gradient descent is not going to use a mathematical formula to solve for these two values. It's going to do it in a little bit of a different way. All right, and here's our line of best fit as calculated. Looks good. Looks like the line of best fit, right? All right. Our different error functions. Mean absolute error is, on average, how far off, plus or minus, are our predictions in terms of dollars, right? So we're about off by $37.6 thousand. Root mean squared error is a similar metric. It is also in terms of the units of the mean, but it's more sensitive to outliers. So if we have these points that are really far off from our trend line, which it looks like bigger homes tend to either have lots of square footage but be crappy homes or low quality. Maybe these are loans that are being foreclosed on because somebody bought a house that was too big and they couldn't afford it, something like that. But for whatever reasons not captured by our current model, big homes are either valued way above our trend line or way below. We might be considering those outliers, but really maybe we just don't have enough X variables to capture the variation that would explain those outliers quite yet. But in the presence of outliers, the root mean squared error will be higher than the mean absolute error, even though they use the same units. The units here is dollars. It's the same units as our Y variable. And then the mean squared error is not in the same units. It's basically the mean absolute error squared. Not exactly, but that's fine. And that's why it has such a big number, right? Any of these metrics is a good and useful and usable way that we can quantify how close are our predictions from the real thing. How far off are our predictions from the real thing? And we then made a graph of a function based upon these error metrics. So to remind you, we'll pick mean absolute error. I think last week we might have used mean squared error or root mean squared error. We're going to use mean absolute error today, just because, okay? And we're going to generate 10 random slopes, but we're going to hold the intercept fixed for 10 times. We're going to calculate the mean absolute errors for all of those, plot the mean absolute errors on the y-axis against the slope values, and you notice this nice quadratic form. And we like quadratic shapes to functions because that tells us there is a minimum and that there's exactly one minimum. And if you know the equation for this quadratic, you can solve directly for that minimum using a derivative. Take the derivative of the function, set it equal to 0, meaning where the slope is 0, and that will tell you the slope parameter that leads to a value of 0 here. And that's what OLS is doing, ordinary least squares linear regression. That's kind of what we talked about last week. We're not as interested in that today. We're interested in, if we couldn't solve for the minimum directly, how could we get there? How could we get there, right? We'll do the same thing with our intercept value, our second parameter. Remember, our model just has 2 parameters, the slope and the intercept. If we pick 10 intercepts at random and hold the slope constant but change the intercept, we'll get something similar. We'll see that the intercept value also follows a quadratic shape, and which is why ordinary least squares can also solve directly for the intercept. But again, we're not doing that today, right? And so putting those two things together, those two quadratic forms, well, notice we have 3 variables here. We have the mean absolute error, that's 1. We have the intercept, that's 2. And we have the slope, that's 3, right? If I want to put all 3 of those things on a graph, they're each going to need their own axes. So if I want to put them all on the same graph, let's see, make sure I've run all these cells here. I might need to make a 3-dimensional graph. So I'm going to do the same thing here, but instead of generating just 10 data points, I'm going to generate 500 of each. We're going to get 500 different combinations of slope and intercept values, and we're going to plot those combinations of slopes and intercepts against their corresponding accuracy, their corresponding quality of predictions, which is what mean absolute error is all about, right? So plot those against each other and we get this cool graph. Okay. This graph is the loss function. Okay. Now, it's not exactly these dots. These dots are just sitting on the surface of the loss function. The loss function continues forever in every direction. Okay, it goes to negative infinity and positive infinity. But we just have sampled some points kind of in the center of this loss function and plotted them. And you can see we've got this nice quadratic shape. We also have a second quadratic shape, but it's a little bit harder to spot. And the difference between these two is driven by the fact that our slope values are like in the hundreds. Like I believe our model's optimal value is like 107. Whereas the intercept values are like in the tens of thousands. So pretty different scales for those two parameters, which is why the second parabola here is kind of hard to see, but there's a slight curve at the bottom if we turn this 90 degrees. And that is the second parabola here, right? These points on the edges are a little bit higher, and in the middle, that's where we see the minimum, right? So this really is kind of a bowl-like shape, just that it's a lot steeper in one direction than it is in the other direction. But we have two kind of intersecting three-dimensional parabola quadratic thing going on here. Okay. And what we're going to figure out today is we're going to write an algorithm that can solve for the minimum value here without ever knowing what our linear regression equation looks like. It just needs our model that can make predictions along our line of best fit, and a loss function of our choosing, which we're going to continue to use mean absolute error. We may, at one small portion today, switch to the sum of squared residuals, which could also do the same thing, right? But this is the picture I want you to have in your head, and our goal is to figure out what is that bottom number, what is that minimum number, what is the best combination of what I'm calling P1 and P2, P1 being the slope, P2 being the intercept, right? That gives us the lowest MAE, the lowest error, right? Error is bad. We want less of it. So we want as little error as possible. Where we have the least error, that's where our predictions are going to be the closest to the true values. That represents our model's making the best predictions it possibly can on average. Okay. So we're going to work with this kind of a graph a lot today. In fact, we're going to work with a couple of different versions of it. But before we jump ahead, I want to switch over to the iPad for a minute and discuss kind of the main themes behind gradient descent. Now, as I do this, some of my screens may be a little bit messed up. I might have to resize them. Just bear with me. I'm still getting the hang of switching devices here with my streaming tools. All right, let's try this. All right, got to make this bigger. There we go, something like that. Let me know if you can't hear me or can't see my screen. We're going to give this a shot. I'm going to move my keyboard and mouse real fast so I have a better surface here. Okay, so we have a graph here. We're going to first start off with a gradient descent example that's not three-dimensional like the graph I just showed you, just two-dimensional. Take one point of confusion out of it, right? So on our y-axis over here, right, this is our mean absolute error, right? And so the lower we can get on this graph, that is good. And the higher we get on this graph, that is bad, right? We want the lower we get with mean absolute error, the better our predictions are going to be. So our goal with gradient descent is always get to the lowest point on whatever function we happen to be working with, bar none. Okay? And we may have a function that looks something like this. I don't like that function. Let's try again. Okay, kind of quadratic, not exactly quadratic. It doesn't have to be quadratic. It can really be whatever shape you want, as long as it's kind of continuous here. Okay, and we're gonna think about this with a little bit of an analogy. I want you to imagine that you are hiking through the mountains. It's a snowy mountain range, and you're right here. Okay, you're literally on this purple mountain contour, and it's been snowing, so the mountains are covered in snow, and it's clear skies, and you've been hiking all day, and you weren't wearing any eye protection, and all of a sudden, you go snow blind. You go snow blind, right? Which is a rare thing that can happen, where you just go blind somewhat instantaneously if your eyes get overwhelmed with all the light reflecting off of the snow. This happens to people, researchers in Antarctica and stuff like that, right? Let's say that happens. So you're here, you're in the middle of nowhere, you're in the snow, you're in the mountains, and you suddenly lose your sense of vision. Well, you know that your base camp or your cabin or whatever is your safe place is here at the bottom, okay, of this valley. Oh yeah, okay. That's our little cabin. You know that your front door that you want to get back to is at exactly the minimum spot of lowest elevation in the whole mountain range. Okay, but you have gone blind. You've lost your vision. How are you going to find your way home? You can't see what direction you're facing in. You can't see where it is. But if you know where you're at, well, you can feel around where you're at, and if you know that one truth that going down is best, going down is the fastest way back home, well, then you can kind of feel around yourself and feel, in the, 2 feet around yourself in either direction, get on your hands and knees, whatever you have to do, and you can feel where is the steepest downwards slope. All right, so I'm going to mark the slope here at your feet with like this tangent line. Okay, we'll say that that's the slope. Okay, and as long as that slope is, in this case, this is a negative slope. Okay, that's a negative sign. It looks like just a line, but it's a negative sign. And that means you need to move to the right. Okay, so if we have your position here on the x-axis, and we say maybe this is position 2, this is position 5, and over here is position 8, right? You need to move from 2 to 5. You know that the downward slope is going to tell you what direction to move, and it's telling you you need to move to the right, right? So we could take your position, your current position, so we'll call that your position in time t. It's the current time period. And we want to subtract from that the slope. That t looks like a plus sign, doesn't it? Let's just say position minus slope. And what's the slope here? Let's say that let's say your current position is 2, right? And the slope is -1. Okay. Well, then that means you, by going downwards, you're going to move to 3. You're going to take a step forwards of 1 unit, 1 distance unit, okay? And you're going to step down the hill to this new location, okay? So you've moved down. You're still blind. You're still hoping you'll be able to get home, but you're at this new location. So what do? You know you're not home yet because the ground's not flat yet. Slope's not 0. So you look at the slope again, another tangent line. And this one's even steeper than the last one. It tells you, whoa, you're really far from home because your home is on flat ground, and this is even further from flat ground than the previous spot. Uh-oh. Let's do that. There we go. Okay, so now your position is 3. And the slope here is maybe minus 1.5. Right? And so that's going to move you to 4.5. You take another step. And this is kind of silly, but you're taking a pretty big step. It's not really to scale with your body, okay? But then you'll be at 4.5. At 4.5, what are you going to do? Well, the only thing you can do, you're going to feel around and you're going to say, okay, am I on flat ground yet or not? Well, in this instance, your slope is a little bit less than -1. Okay? Our tangent line this time would fall below the curve, which is good. That means that you're bottoming out. Let me even do that in a different color. Okay, here's your tangent line now. I'm totally guessing at that tangent line. Okay, but that tangent line, now that you're in position 4.5 minus, I don't know, we said it's a little bit less than 1, right? Because it's below the line, so maybe it's minus 0.8. And that means you're going to take a step to, what, 5.3? Which is actually a little bit past your house. Okay, that's here. And you take another step. You go past your house a little bit. And you start to feel the ground goes uphill again. You go, oh no, this tangent line is now uphill. I must have gone too far. I keep on accidentally deleting things I don't want to delete. It's a very sensitive eraser. Okay. Okay. So this tangent line is pretty flat, but it now has a positive slope, right? So you do the same thing. You take your current position, 5.3, and you subtract the positive slope. Let's say the positive slope is 0.3, and you get to 5.0, which is exactly where you wanted to get. So your final step is to your front door. Okay. What happened here? The only thing you knew was what is the slope that you're on, and you took cautious steps based on what took you downwards. All right, what took you towards the minimum of, you know, the topology here, the area, the mountains, the function. Okay, and we took some pretty big steps, right? You ended up being like 3.5 steps from your front door. It's a little bit exaggerated, right? If you're really blind, you know, out in the woods, you would maybe be, if I clean this up here. All right. You would maybe take one tiny little baby step and say, okay, it's still downwards, and then another little baby step, still downwards. And then it gets really steep. You're like, you get a little more confident that you're nowhere near home. So maybe you take, when it's steep, you take a little bit bigger steps. But then as it's shallowing out, you're like, oh, I'm getting close to home. I better not miss it. And you slow down and you take smaller and smaller and smaller steps. Well, this is gradient descent, right? We're going down this gradient. We're seeing where am I at on the curve, or what is the slope where I'm currently at on the curve, and using that to guide us downwards towards the bottom. And this is the same intuition, the same approach that the gradient descent algorithm takes. Okay? And the equation that I had up here on the board, which was, right, your current position minus the slope, that is the important concept. Your current position minus the slope, and if you do that iteratively in a repeated fashion, you're going to end up at the minimum. Okay? That's kind of really all there is to gradient descent, but instead of it's in the context of a hiker, this is in the context of, well, we pick some parameters for our model, right? Maybe this is, instead of position, this is now the slope parameter. And I start off my slope over here at a value of 3. And that's not quite right. That's too steep, right? So whatever my current value is, if I've got a negative slope, I need to move to the right. Subtract a negative is going to make this bigger, and I'm going to take some step to the right, right? So negative slope is going to move us to the right, and a positive slope is going to move us to the left. And that's kind of really all there is to it. Well, in two dimensions, that's all there is to it. But what if, and instead of erasing this, let's just go back out. Switch screens again. See if I can do this. Okay. In 3 dimensions, it's not quite so simple, right? So in the 2-dimensional graph we just saw, we had exactly one parameter. The x-axis was our one parameter, and the y-axis was our error metric, mean absolute error. Lower is better, higher is worse. Well, in this 3-dimensional form, we can see both parameters, p1, the slope, and p2, the intercept. Okay? And let's see here. We calculated, trying to find a good, we calculated the slope, the rise over the run. At my exact position right now, what was the slope? And the way to find the slope at an instantaneous point, we use a tool called a derivative. But this is not a derivative where we're solving the whole equation for where it equals 0 for all parameters at once. We're just looking for one single parameter. What is the slope of this function in regards to parameter 1? With respect to parameter 1, or what is the slope of this function with respect to parameter 2? And if you've taken a little bit of calculus, those sentences might make sense. If not, I hope to help them make sense as we talk here. Right? But all that a derivative is we take a pair of points. We can easily find the slope between, the average slope between them, and we slide one of them closer and closer and closer to each other. And as we do that, as that distance between those points gets smaller and smaller, well then the slope between those gets closer and closer to the slope of this dashed tangent line, which is what we were really after. That is the slope of the function at the point C, f of c. Okay. And that's really all a derivative is. It just tells us the slope of a function at a specific point. Okay. Well, that is the case if our function is 2-dimensional. If our function is more than 2-dimensional, 3-dimensional, instead of calculating the slope, we say that we are calculating the gradient. So a gradient is really just a multi-dimensional derivative. If you take a little bit of calculus, we take a partial derivative with respect to whatever parameter we want to, well, remember that each slope is going to tell us, do we want to move left or right? Well, we take the derivative with respect to that specific parameter. The derivative ends up being positive or negative, and it tells us, hey, should we move that parameter left or right? We start off with some, could be totally random initial values. we could pick any starting point anywhere on the loss function and walk our way step by step by step to the minimum. So it doesn't matter where we start. The closer we start to the minimum, that's cool. The faster we'll get there, the less steps we'll have to take. But we should be able to get there from anywhere. Okay? What we're going to do is, as we take a partial derivative, it's as if we were kind of taking a cross section of our function here to isolate just one of the parameters and then finding the slope, or similarly that quadratic. Okay, so long story short, all that a gradient is it a calculation of slope in a multi-dimensional space, bigger than 2 dimensions. And our loss functions take on this multi-dimensional nature when we have more than 2 parameters. More than 1 parameter. Which with simple linear regression we have exactly 2, which is barely more than 1. Okay. And so then what do we end up doing? This is a fancy calculation that all that it really saying is what I was saying is, right, our new position is going to be our old position minus the slope. There's a couple of other things going on here, but that's basically what's happening, right? The position of the next iteration is the position of the previous step minus whatever step in whatever direction we're going to take. And that's what gradient descent does. There's also another little wrinkle here called the learning rate. We'll get to that in a little bit. The learning rate can basically scale up or down our steps and say, hey, you're on a really steep part of the gradient. You feel free to take a bigger step right now. Or, oh, you're on a kind of flatter part. Let's take a smaller step to be more careful. And we can tweak the learning rate. The learning rate is determined by us, the data scientists. We'll indicate the learning rate before we even start the algorithm. And we'll try and find the learning rate that is the most optimal, but all that it does is scales up or down the size of step that we take. It doesn't change the direction that we're stepping in, just changes how big of a step we're willing to take. So even with the learning rate involved, it's still the same basic concept of your current position, move in some direction, move left or right, and that left or right movement is based on the sign of the slope. Is it a positive slope or a negative slope? Positive slope, we're going to move to the left. Negative slope, we're going to move to the right. That's really all there is to it. We're going downwards in both of those scenarios. And we're going to keep on taking those steps over and over and over and over again until we get to the minimum. So this is a giant case of guided guess and check. Guided guess and check. Okay. Start some initial position, calculate the gradient, aka slope. That tells us how big of a step to take. And as that slope starts getting flatter and flatter and flatter, we're naturally taking smaller and smaller steps as we get closer to the minimum, because the slope is getting closer and closer to 0, right? And when the slope is at 0, that's when we're at the quote unquote global minimum, which is what we're after. That's when, if our y-axis here is a measure of how good our predictions are, or excuse me, rather a measure of how bad our predictions are, we want to have the least bad predictions. We want to be as low as possible, right? So it's the point. It is the combination of parameters that is going to give us the least bad predictions. Or in other words, the best predictions we could possibly have. Okay? So if we have a way of calculating how good my predictions are relative to the ground truth in my original data set, I have my y values in my data set. That's why I'm doing supervised learning here. My model makes some kind of predictions. If I can quantify how good or bad those predictions are, that's going to generate a loss function, which I can then traverse to find the optimal performance of my model. And that's pretty much just gradient descent. You're just walking down a function. You can also think about it as a ball rolling down a function, right? If I put a ball on this side, what's going to happen? It's going to roll downwards. It might overshoot the middle a little bit, but then it's going to roll back, and it's going to wind up being at the minimum, right? So whether you think about it as a blind hiker or you think about it as a ball rolling down the function with some kind of momentum that's determined by, the steepness of the gradient, works great. But that's what gradient descent is doing. And as we talk about this later, in the context of neural networks and things like that. We'll talk about, there's actually a lot of variants of this algorithm with different pros and cons. And here's a few of the popular ones with TensorFlow. And notice they're all trying to find the minimum. Some do better than others, right? This is a tricky gradient because we have here in the middle what's called a saddle point. A saddle point is where the minimum in one dimension is also the maximum in another direction. Right? So in one direction, that's the maximum. In another direction, that's the minimum. And it's sometimes tricky for the models to get out of that rut and figure out where to go. So you notice some of them pause for a minute before they gradually shake themselves to one side or another. But SGD, stochastic gradient descent, which is kind of the vanilla form of gradient descent, which is probably the closest thing to what I'm showing you today. It gets a little bit confused here, gets stuck. But that's okay. We're just laying the groundwork, establishing the basics today. This isn't going to be the most amazing implementation you're going to see today, but we're going to learn the intuition. We're going to learn exactly what is this function? What is this thing doing? Okay. So another thing you'll see commonly when people are talking about loss functions is they'll use contours to describe how close to the center a particular combination of parameters is, right? Down here in the very middle, the very bottom, the very minimum, that is the set of parameters that is the best model possible. In this example, that would be 0, 0, right? It's centered at 0, 0, okay? And if I'm off, well, gradient descent's going to walk down to the minimum, okay? But the reason why I show you this in these grid lines is kind of like a topographical map. I don't know if you've seen these in the past, but these are our maps that are used to try and show height on a 2D plane, on a page of a book or a map or something like that. Let me open this in a new tab. Right? And each of these lines represents some elevation change, maybe like 100 feet of elevation change. So where these lines are closer together, that is where things are steeper. And where the lines are farther apart, that's where things are flatter. Okay? And wherever you see a circle, that's either a peak or a trough. And I'm not sure which. I think this is a peak because it's labeled Gray Peak, right? So that's the very top of Gray Peak. That's the top of Mount Marcy. There's the top of Little Haystack. I don't know where these are. If you're from here and recognize these mountains, that's awesome. Okay, but this is a topographical map, and our contour plot is the same thing, but instead of for mountains, it's for loss functions. Okay, so I want to do something. I want to imagine with our loss function here, well, if I can, what would the contour map look like? Well, first off, we have to be looking at it directly from above. Directly from above. So that mean absolute error is the height that's coming up at us. Okay? And you can imagine like some kind of concentric ovals where that minimum would be here in the middle and then it would grow outwards and outwards and outwards. Let me switch screens again and see if I can draw that for you just to maybe really drive it home. Let's see here. Okay. Gonna erase things. So if I had to draw a contour map here, okay, where this is P1, that's our slope. This is P2, that's our intercept. And mean absolute error is coming up at us vertically out of the paper, out of the iPad, which is what I'm drawing on here. Okay, and our minimum is somewhere in this very center circle. Maybe the very central point of that center circle. It's right there. That's not really the center, but we'll call it the center. And then there's these concentric ovals coming outwards. And in fact, I should, they're going to start off a little bit wide apart from each other. And the further out we get, the closer together they're going to get because the walls of this function are getting steeper and steeper. I'm not a perfect artist, but something like that, right? So this is a way of trying to represent in a two-dimensional format our three-dimensional graph. And with a lot of these graphing skills and these graphical representations of our functions, we're limited by our human abilities to only understand things in two-dimensional space or three-dimensional space, which is why I wanted to talk about this today when we're working with a model that is operating in 2/3-dimensional space. Okay, so if we look at a contour map for linear regression, here we go, this is a little bit better one. All right, this is our three-dimensional version on the right, and this is the one I was trying to draw for you with my poor drawing skills, right? They are the same information, they're the same graph. We're just, this one we're looking down at it from above. We're looking at it from on top versus at an angle. Okay. And the only reason I belabor this is because you're going to see both of these representations later on when we talk about regularization techniques for these linear models like bridge regression, lasso regression, elastic net regression. We're going to revisit these contour plots, and they're going to be important to us. So having a concept of the loss function and these different graphical representations of it is going to help us in the future. But it's cooler to look at it at an angle, right? And it's even cooler to have this 3D, zoomable plot. That's way better than a contour plot, right? So technology for the win, I guess. There we go. So one thing you need to know is that these contours, plots, these topologies, these gradients can have really different shapes to them. Now, whenever we work with linear regression, our linear regression gradients are always going to be what's called convex, like this one on the left. That means they have exactly one minimum, which is part of why it's so easy to solve for that minimum using math and equations and algebra and calculus. But when we get to more complex models, like neural networks, we'll many times have non-convex gradients. And with these non-convex gradients, you'll notice that there's actually multiple minimums. We have what's called a local minimum, and then we have the global minimum. The global minimum is, of all the minimums, that's the lowest one. Local minima are troughs that we could get stuck in, but that are not the very best set of parameters that we could get to, right? So we might get stuck in this hole and not be able to find our way out. We might think, hey, I reached the cabin. I'm at the bottom of the hill. I'm on flat ground. Isn't that where the minimum should be? When really it's a local minimum and not the global minimum. So this is actually a challenging thing in the world of neural networks, and there's a lot of different techniques we can use to give ourselves a leg up in these kind of contexts. And in fact, some of these linear regression optimizers exist exactly for that reason. Some of them that are pretending to be balls that have momentum. So if they roll down a steep hill, they'll gain some, where am I? Did I close out of it? Oh, it's here. They'll gain some momentum and be able to maybe find their way up and out of small local minimums and then up and over this hump down to the other one. So if you think about a ball that's rolling, it's got some inertia, it's not going to want to stop. And some of those forces are mimicked by some of these other gradient descent based optimizers. Not so much by stochastic gradient descent, today's model, but they're all kind of variations on this theme that can lead to improved performance in the face of some of these challenges. And there's like about 27 other things you could do to improve it here. One of the things we're going to talk about is the learning rate. Choosing a good learning rate can help with some of these some of these issues. And yeah, we'll get to that in a little bit. Okay. So I hope I have overemphasized the intuition here, and you're like, all right, Ryan, we get it. We get kind of what gradient descent's trying to do. Let's use gradient descent to solve and find the minimum, to find the two best parameters of our linear regression model without solving for it directly. Okay? And we're going to do a couple of different code implementations of varying levels of sophistication. Even the most sophisticated one today is not going to be like that great, because this is mostly for demonstration purposes. I want you to be able to follow the code and follow what I'm writing, more than having it be like the fanciest, best, coolest code ever. So if you're like, oh man, this is sloppy, that's partially intentional, partially just because I'm a little bit sloppy sometimes. But okay, so before we really implement a gradient descent here, I want to show you a couple more graphical tricks that we can use. All right, really just to drive home, what is this loss function? What is its shape? What is it all about? And I may copy and paste here a little bit. In fact, I think I am going to. Okay. For starters, I want to remind you what the scikit-learn version of our model says are the best possible parameters, right? So we'll save this as P1 true. Remember, I'm calling P1, that is the slope parameter, and P2 is the intercept. And then let's print those. Sometimes you'll hear people call the slope one of the model's weights. And the intercept, they'll call it the bias. Those are kind of more neural network type terms, but they apply here. Okay. So this, and the reason why I bring that up is later on, you'll see the slope and intercept not referred to as P1 and P2, but you'll see them referred to as W and B, weight and bias. So just bringing that up so that when we come to that, hopefully that's less confusing. Okay. And what I'm going to do is, instead of doing a random sample of points around the minimum, I want to get an orderly grid of points so we can really see the contours here. And that's also going to help us see the derivatives of the slope and the intercept on their own, those partial derivatives. So what I'm going to do is, our true y value is 107. So I want to go from 107 minus 10 to 107 plus 10 and count by ones. And what this is going to do is it's just going to generate a list of numbers from 97 to 117, 216. Okay. I believe this is 20 numbers here. Okay. Because I want to make a nice even grid. So you want these values to be evenly spaced. So these are the slopes. These are all the different slopes we're going to use. And if I print them out, they will print out horizontally rather than vertically and not take up so much space in my notebook. And we're going to do the same thing for intercepts. The intercept is 18,569. We're going to round that a little bit. We're going to pretend that the intercept is actually 18,600. And we're going to subtract 500 from that for the lower bound. If I can type here. And add 500 to that for the upper bound. And then we're going to count by 50s, so we should get the same number of points. So we should have the same number of slopes as we have intercepts. Evenly spaced all along this range. And now if I look at every single combination of slope and intercept, I'm going to end up with a whole grid of points. And then if I plot all those points on my loss function, all these combinations of parameters, I'm going to get a grid-ish looking set of numbers on the loss function. So I've got to calculate all those different combinations. And I'm going to let I'm going to let Colab do some autocomplete for me here. For P1 in slopes, for P2 in intercepts. And I want to append here, actually, let's append a dictionary with key value pairs P1, P1, P2, P2, and MAE using our MAE function. I think that looks good. I think we're missing a curly brace though, right there. And we're also missing a parenthesis. Because I have a closing curly brace there. There we go. So how many points should I have here? Well, I should have length slopes multiplied by length intercepts number of points. So I should have 400. And if I look at points here, that's what I should have. And I do. So I have every single combination of slope and intercept that I possibly could have. We're going to plot 400 different points on this loss function, but evenly spaced points. So for ease of plotting, I'm going to put these in a data frame. Okay. So I have the slope, intercept, and the corresponding mean absolute error for all of those. And now those are the three things I'm going to put in my scatter plot. Yeah, P1, autocomplete for me. Sure. Okay, looks a little bit different, right? This is exactly the same shape. It's exactly the same loss function, exactly the same contours. I've just picked different spots on it to put my points. Rather than sampling kind of in a circle around the minimum here, which is what I did previously, picked a grid of numbers. And the reason why I think this is going to be more helpful is we can look at the gaps between these points to get like a rough estimate for slope by just comparing 2 points to one another, holding P1 constant there. See how P1's not changing between those 2 points, but P2 is. So I can use the difference in P2 and MAE here to get an estimate for the slope of MAE with respect to P2. And I can use the difference between these 2 points vertically that should have the same P2, but the P1 is changing to get an estimate for the slope of P1. Okay, so that's kind of my partial derivatives here. I can kind of fudge it a little bit without doing a fancy derivative calculation. I can get in the ballpark of the slope. It doesn't have to be exactly right. And that's how we're going to kind of roll our calculations here. Okay. So that is one thing I want to show you. The second one I want to show you is, well, what if I didn't sample points on this line? What if I just drew the whole contour? Okay, so this is me doing that. You don't need to know anything about this code. I just wanted to show you kind of what it looks like. This is using what's called a mesh grid, and this is the loss function, all filled in. Okay. And this is me just sampling from the loss function at even intervals. But it's the same shape. Okay, we on board? We with each other? Different ways of plotting. Plotly is pretty cool. I recommend taking a look at it if you've never used it before. Okay, so now let's do our implementation. The first step with gradient descent is to pick initial values for our parameters. Now it really doesn't matter what we pick. We could pick 0 for both of these. That's totally fine. But I'm not going to do that. I'm going to pick something that's in the ballpark, something that's going to show up on our graph. So I'm going to pick 115.5 for the slope and 19,000 for the intercept. Okay. And then we need to choose a loss function. We know that we're going to be working with mean absolute error. See if this fills in the rest for me. Doesn't look like it's going to. Why is it not doing that? Sure. Okay, so there's the MAE. Okay. So if I plot this point, 115.5, 1900, 39,971 on my graph, which I'm going to do, I'm going to turn it into a point, and I'm going to use a dictionary again, but I'm going to call this slope P1. I said I was going to make this a dictionary, and then I didn't put curly braces on it. There we go. So there's our point, now held in one single container. And that makes it really easy for me to graph it. So I've got my graph from above. We're actually going to use this one. And to that same figure, I can do what's called adding a trace, which just means add something on top of it. It's kind of a plotly way of saying it. And I put in my x value, my y value, my predictions. I don't know why I made a dictionary here if I was not going to use it here, but I'm actually going to leave this hard-coded. I think it'll be a little bit easier to see what's happening if I leave it hard-coded. So I guess this was not needed. Okay, but here's what it looks like with me plotting my initial starting place. Okay, this is where my blind hiker is starting. It's at this blue dot, okay, which just represents the model's quality of predictions given a specific set of parameters, given a specific slope and intercept. Okay. So what do I need to do? Well, I need to calculate the gradient with respect to each individual parameter. So I'm going to get what is the slope when I look at just the mean absolute error and the P1, and what is the slope of my loss function when I just look at the mean absolute error and P2. Okay. So let's think about that. And if we look at our graph here, okay, if I want to get the slope, I think it's actually like this, right? So the first thing to do is look at your axes and make sure you're looking at it in the way that makes most sense to you. So I want low numbers to be on the left and high numbers to be on the right, and low numbers to be low and high numbers to be high. So this is going to help me reason about it. Okay. And these back 2 points, this is P1 equals 116, this is P1 equals 115. So rise over run. If P1 is increasing by 1, what is MAE changing by? Well, MAE is going from 39,772 to 40,207. So that is a run of 1 and a rise of 400 something. Okay, so let's calculate that slope. So, all right, the change in P1 is 1, or in other words, it's, oops, it is 116 minus 115. And the change in MAE is 40207 minus 39772. Right? So that's change in one axis, change in the other axis, which gives us slope. So we're going to call this the gradient P1 is equal to the change in P1 divided by the change in MAE. Okay. And that is not the right value. I've got my numerator and denominator mixed up. And I don't think that's the right value either. This should be 39772. There we go. So it's about a change of 435. That is a really steep slope. Okay. And if we're looking at it from this direction, right, what we're saying here is the slope at that point is 435. We're going up $435 of worse prediction for every slope value to the right. So remember that this slope is the average cost per square foot. So if I say the average cost per square foot is actually $116 rather than $115, then my predictions are going to be $435 worse on average. That's what this is saying. Okay? So because this is a positive slope, remember, positive slope means move to the left. So I'm going to take my current position, which is, I guess we're going to do that down here, right? My current position is P1, and I'm going to subtract gradient P1 from that. No, that's not right. Actually, I'm going to take P2 and subtract gradient P1 from that. There we go. So this is always a little bit confusing, is because the way I've labeled these is a little bit different. This is the gradient of P1 is with respect to P1, but it tells us how to move P2, which is a little bit confusing. It's a little bit confusing. And this is one of the easiest ways to slip up the implementation, which honestly you're not going to be rolling by hand very often, but I hope this helps you understand it, right? So we were at our original position for that parameter was 19,000. And once we calculated the gradient, subtracted the gradient, we moved 435 to the left. This is our new location. We took a step to the left, 435 units. Okay? And we're going to do the same thing with P2. But with P2, we want to look at this in this direction. Now I want P2 to be in my x-axis and MIE to be my y-axis. So, and I can pick any 2 points. I'm going to pick these yellow points back here because they're the closest to my point. So my P2 is going from 19,050 to 19,000. Okay, so let's see. So that's 19,050 minus 19,000. And then my change in my MAE is, I could directly calculate it, but I'm going to look at this here. So from 40207 minus 40192. So 40207 minus 40192. Okay, my gradient is 0.3. So for every 30 cents per square foot that I change my estimate by, say, oh, it's not $116 per square foot, it's $115.7 per square foot, right? My MAE is going to improve by $15 on average, right? But if you're making lots of predictions, that adds up, okay? So notice that this is a pretty small step, right? I need my slope parameter to go from 115.5 all the way down to 107. So I need it to go down by about 8, but I'm only taking a step to the side of 0.3. So this is going to, if I keep on taking steps of this same size, it's going to take 24 to 25 steps to get down to the minimum. But I know those steps are going to get smaller as I get down to the minimum because the gradient's going to get smaller. The slope is going to get closer to 0. So what I'm saying is this is going to take a lot of repeated steps for us to get what we want. So this should be P2 minus gradient P1. Nope, this should be P1 minus gradient P2. There we go. And there's my new position. These are my 2 new parameters. I've just taken a step, right? And this is my new location. Let's graph our new height on the graph at that new location. And we'll just immediately put it on the graph. So here's our old graph. But we're going to add a new dot to it. And that new dot is going to be at position 115.2 for slope, 18,565 for y, and whatever that MAE comes to. I'll let it calculate its own MAE. which is why I was going to leave it hard coded so I could just do that copy paste and it would be done. And that's not right. These 2 points should be much closer to each other. I think I have a typo of some kind. Instead of going way off to the side, this point should be going down towards the middle. Should at least be trying to. If I copy and paste from my notes, I think I just have a silly typo in here. Oh, maybe the typo was up here. There we go. That looks much better. Okay. So we've taken our first step. Here's our first position. We moved to the second position. Now, what do? Well, we do it all over again. Okay. And I'm just going to copy and paste for this because you've seen it, right? Our change in P1, we're now going from 115 to 114, right? Or maybe I should just go 115 to, 115, 114, thereabouts. So that's my gradient. What did we call this? I want to make sure we match our variable names. Gradient P1. Change P1, change MAE. Okay, that looks good. And we're going to do the same thing for P2. Change all these to P2. And the P2 is going to change by 18,950 to 1890. Change of 50. It's always going to be a change of 50 if I use those points. Oh, excuse me. This should be up. This is wrong. This should be here. The change in the MAE is what? 39745. I zoomed out on accident. To 39731. So there's your gradient. It still went down by about the same amount. Before it was 0.3, but it's slightly smaller now because we're on a slightly flatter part of the wall. It's not as steep anymore. So both of these steps are a little bit smaller because we're getting to flatter and flatter parts of the curve. It's still pretty steep, but it's getting flatter. Okay. And what should our new position be? Well, it should be our old position, which was, notice this is a lot of repetitive code saying this is not a good implementation. We're gonna make this more generalized and programmatic here in a minute. Those are my two numbers, right? So this is 18,950 minus gradient P1 and 115.2 minus gradient P2. And those are my new locations. All right, now we can graph and fill in these values. Now we've just taken a new step. And again, it's very off, which tells me I have a typo. Yeah, this is way too big. Why is this 189,000? This should be 189,500. No, should be 118,985. Okay. So just added an extra 10,000 to this number on accident. No big deal. That is a big deal in terms of our loss function. And that is still way off. Tells me I've still got a typo somewhere. 114.92. Oh, I'm subtracting the wrong numbers from the wrong ones. I think I did the same thing above. So it should be P2 minus gradient P1 and P1 minus gradient P2. And I think I have those backwards. I'm even getting my own brain twisted around. No, that should be about right. But what's going on here? It should be right there. Let's do this. I'm just going to copy from my notes instead of searching for this bug, taking your time. And this is not going to exactly match what we had above. I know that's the right point, but I'm not sure why these numbers are so different. I think I looked at a slightly different pair of numbers for estimating it here. So let me just substitute that. That way it will match. All right. Same thing. That's the correct point. So we've now taken 2 steps. Yay. But we got to keep going and going and going and going until we get to that minimum, right? So if we're doing the same code over and over again, our code's repeating itself, which we don't want it to do. We want our code to be dry. Stands for do not repeat yourself. Well, we can do one of 2 things. We could do lots of iterations, or we can take bigger steps. And one of the ways we can take bigger steps is by multiplying our gradient by a learning rate. And that can lengthen our size of step or shorten it. And in some instances, we might want to do either or, right? But we have to be careful. If our learning rate is too big, then our model's going to take a step all the way across the function, and then all the way back, and then all the way across, and it's going to actually go outwards and diverge. It's going to move further away from the minimum rather than towards the minimum. If our learning rate is too small, it's going to take too many iterations to get to the minimum. So we're kind of looking for this sweet spot, this Goldilocks zone, so to speak, with our learning rate, and being able to multiply our gradient by some constant learning rate. Well, it doesn't have to be constant, but we're going to use a constant learning rate for today before we add or subtract it from our position. And that's going to either lengthen our stride or shorten it. Either make it so we take tiny little baby steps, or so that we hopefully take more regular steps. Okay? Now, this is going to be a little bit tricky because we are actually, because our P1 and P2 have pretty different units. P1 is measured in hundreds, and P2 is measured in tens of thousands. And that might make this a little bit tricky here. Typically, we would want to do something called normalizing our data, which is going to make it so that it all has roughly the same scale, and that will make actually make gradient descent's job a little bit easier. But I'm resisting doing that for today. We're going to actually do that next time we talk. So, and I'll come back to this and tell you why we're doing that. But if you see that we're using like a wonky learning rate today, and maybe you have experience with learning rates, and you're like, whoa, that's really weird, Ryan. That's why. So just a heads up. And you might not even notice. You might not care either. So, but here's what we're going to do. To remind you of our loss function and our predict function, I'm going to move them down. We have these up above. I'm just rewriting them here. Okay. And then our current position is here. Okay. And I want to do, instead of just the 2 iterations that we've done, I want to do 200 iterations. And as I take those steps, I want to save my values for P1 and P2 so that I can plot them on the graph later. And I want to save the loss, my mean absolute error, my height, so I can plot that on the graph as well. So we're going to capture those as we walk down with gradient descent. So as we go through each of our iterations, okay, each time we're going to calculate our loss for whatever our current position is. Okay. And then we're going to calculate our gradient, or what we want to change the P1's MAE by. So this is kind of our gradient. And programmatically, this is where the things get a little bit wonky too, is I'm going to just, I'm still not calculating a derivative here. I'm going to weird lengths to not have to show you the derivative calculation. I'm just adding 1 to my x value to get the slope. So if I move my x value by 1 and calculate the MAEs, take the difference of the MAEs in both of those, that's roughly equal to my slope here. Okay. We're going to do the same thing with P2. But instead of adding 1, I'm going to add 50. And again, that's because of our different units. Because our slope parameter is measured in the hundreds and our intercept is measured in the tens of thousands. So that's going to, this is a very sloppy, imprecise, but workable way of calculating a gradient, basically. Okay. So my updated position, updated P2 is, well, going to be, oh, so this is sorry, this is my my gradient. That's how much I want to change the value by. And you're saying, Ryan, you're not doing anything. You're just renaming variables here. Well, I'm going to add a learning rate to it in a minute. And then it won't be a variable on its own. But for now, we're going to pretend we have no learning rate. Our learning rate is just 1, right? There's our learning rate. Right there. So it's our gradient multiplied by the learning rate. And that ends up being the update. So I guess this is really our gradient. So yeah, I guess this should be the update. How much we want to move. This is our step size, as it's sometimes called. The total size of step we're going to take in some different direction. I'm just going to call it an update. Okay. And then I'm going to actually change my values for current P1 and P2 to actually move my point to a new position. I'm going to calculate my new MAE. Make sure I've got this right. Okay. And then I'm going to append that new location to a list. So I save all those locations just because I want to make a graph, really. Saving these does not matter unless I want to make a graph. So it's locations plural. Okay, so what's going on here? Starting MAE, calculate the gradients, how much to move by, scale gradient calculations by the learning rate, update the location of our hiker, so to speak, right? Store the locations as we go so that we can graph the path that our hiker takes. Hopefully that makes sense if I call it a hiker. Right? Okay, so that is all run, and I didn't get any errors, which is kind of a miracle. Let's now plot it. I'm going to plot this on top of our 3D graph. So I'm just going to for loop over the locations here and add them as points. It's going to take a second because we have 200 points that we're adding onto the graph, doing a lot of calculations for and adding onto the graph. That shouldn't take more than like 10 seconds though. That looks off. Okay. What I think is happening here is you're seeing an example of divergence, right? The point we started at is in here somewhere. I don't know if I can even zoom into it. Like our starting position is on the graph, but then we took such a big step size that we stepped across the graph and then across again and then up, and we're actually, I don't know if you've seen like those old Hot Wheels vortex thingies where the car gets so much momentum that it throws itself up and out. This is probably a throwback to my childhood and nobody else's, and I can't even find a picture of one, but the car gets so much momentum that it like shoots itself up and out of this funnel. And that's kind of what's going on here. Instead of going down towards the minimum, we're going outwards. And that's because we're taking too big of steps. Okay? So this learning rate can both make our steps bigger when we need to, but it can make them smaller when we need to as well. So let's make those 1/100th the size and see if we get any better results. And I wish I didn't have to wait a few seconds for this to run every time, because then we could like play around with the learning rates and do a lot more. Okay, that's looking a little bit better. We started here and it looks like it is moving down. It is trying to get to the minimum, but it's kind of getting stuck in this saddle point of sorts, but it is moving down. Right? If I, let's see, if I print out our locations here, let's do it vertically so we can just scroll. We should see the MAE dropping. Right, so it starts off at 38,000, then 37.7, 37.6, 37.56. Right, so it's going down. It is, our predictions are getting better. The combinations of slope and intercepts that we're picking are getting better, but we're not getting to the minimum quite right. And I think I may have a typo somewhere. So let's do this. It's going to remove my comments, but we'll see if it works any better. This is from my notes. This should get us a nice looking smooth graph. There we go. That's more of what I was after. So I did have a typo somewhere. Okay. So if we take small steps, gradually zoom right down to that minimum. Okay. Now this is not exactly the minimum. I may not have enough iterations. It might need to be like 220 or something like that for us to get down to that minimum. But we're just using the slope and letting the slope guide us and taking those baby steps downwards. So we went from having too big of steps to maybe these steps are a little bit too small. I don't know. But this is what we call a hyperparameter. It is a setting that has to be determined by the data scientist. It can't be calculated by the algorithm, by gradient descent itself. The learning rate is one of those hyperparameters. It's not something the model can figure out on its own. It's something that I, the data scientist, have to experiment with and until I find a good working value, right? And I've made the points on the outside a little bit opaque so that our hiker's path stands out a little bit more. But that is gradient descent, literally walking down the hill to the valley, to the minimum down below. Okay. I do want to show you a slightly more sophisticated implementation. And I'm going to do lots of copy and paste for this. I don't expect you to, oh, well, pretty much with all the code I've showed you today, I don't expect you to need to recreate it really at any point in time. It's mostly just hopefully so I can visualize, whoa, it's happening. Whoa, it's walking down. Whoa, we calculated the gradient. We multiplied it by the learning rate. We updated the position by the gradient multiplied by the learning rate. And that's really all that's happening here. Okay. But I haven't actually been calculating the gradient yet. I've been doing kind of this hacky in the ballpark slope calculation, which works, but is not really how it's done in reality. So I'm going to use a little bit of fancy TensorFlow function magic, and I'm going to let TensorFlow calculate the honest to goodness true gradient, the partial derivative of the loss function for me, and we're gonna really nail this on the head. Okay. But in order to do that, I need my loss function to be in like TensorFlow language. Okay. And this is the sum of squared residuals. We're going to turn that off. We're going to keep the mean absolute error loss function. So I've got two here. I've got a mean absolute error loss function. I've got a sum of squared residuals loss function. Okay. I'm going to save, I think we have this above, but this is W is my slope, B is my intercept. So that I know what to refer to, I know what the true values are. We're going to use those in a couple of graphs a little bit later on. And then we're going to use a very simple class to make our own model here. All that it's going to do, it's going to hold internal variables for our current position and have a way to calculate predictions, right? So this is our predict function, and this is where we're storing our current position. It's really all that's going on here. TF was not defined. Did I not run this? I didn't run the code cell above. All right. Okay. So if we pick these starting values, which is the same ones we picked above, you're going to see this is actually pretty darn close to the line of best fit already, but it's not the line of best fit. So let's plot that here. Okay. So here's our bad values. This is not the correct slope and not the correct intercept, but it's in the ballpark. So we're actually not that far off for starters. We got a pretty lucky initialized values. We'll say that. And as I train this model, I'm going to calculate my loss, calculate the gradient with respect to W and respect to B, dW and dB. So D being delta, like the change in W and the change in B, Greek letter, right? So it was called dW is the change in W, dB is the change in B. So I'm going to multiply those changes by the learning rate and then override the current position in the model. And I'm going to do that a bunch of times. Okay, that's how my model is going to be trained. And for graphing purposes, I'm gonna again store the locations here in a bunch of lists, just so I can graph stuff later on. And I'm gonna do 500 iterations this time rather than the 220 we did before. Okay, and this is something that is a little bit atypical. I have two different learning rates. I have one learning rate for the slope, one for the intercept. That's typically not the case. Typically you have just one learning rate for the whole model, but I'm doing this so that I can deal with the headache of our slope and intercepts being to such different scales. So know that this is still a little bit hacky, having the two different learning rates here, but we'll see where it gets us. And I think we need to experiment with these as well. I don't think these are the correct learning rates. Okay. So let's take a look at this. We started at these initialized positions, and over 500 iterations, we never moved. And that tells me we're not taking big enough steps. So maybe our learning rate is too small. We need to take bigger steps. Let's start taking really big steps, and we'll see if our model diverges rather than converges. Okay, and you can see some of the bouncing back and forth now. It starts on one side, bounces to the other side, bounces to the other side. Like, it's all over the place. Let's make this even crazier. Let's really make it diverge. Yeah, now it's just bouncing back and forth from negative to positive to negative to positive. It's just hopping back and forth between different sides of the parabola. Just kind of wild. Okay. So it looks to me like our W, our slope parameter, is changing too much, and our intercept is fine. Our intercept's maybe not changing enough. So let's take our slope, which I think is affected by LR1 here. Yeah, change in W, the change in the slope. And let's make that a lot smaller. Okay, we're starting to see some movement in the right direction, right? But we're not getting there in the number of epochs that we are currently running. But the loss is going down. Our predictions are getting better and better and better as we take baby steps down towards the minimum. But this W needs to get down to 107. And we're going from 115.5 to 115.3. So we need to be taking bigger steps than that, but not so big. Okay, now it's dropping. Hey, and it's getting down to 107. Oh, and it's overshooting. Go down to 106. And the reason why it's overshooting is because our intercept parameter is not moving fast enough. And so the slope is trying to compensate for the intercept not moving far enough. If we get the intercept moving, then our slope won't overshoot so far. It went down to 106.15 when we wanted to stop at 107.13. So let's get B moving a little bit more. Hey, there we go. That looks a lot better. It's still overshooting a little bit, but it looks pretty good. And in all reality, we might be getting slightly different optimal parameters here because we're not minimizing the sum of the squared residuals, we're minimizing the mean absolute error. So I'm not overall worried that this is like not exactly the exact numbers that we had before, because we're using a slightly different loss function than ordinary least squares was to directly calculate the best values here. But our loss is dropping, meaning our predictions are getting better, our error is going down, and our slope and intercept are converging upon the optimal values here. Okay. Just to prove it to you that this is truly doing its job, that's why I'm going to turn off our mean absolute error loss function. I'm going to turn on a sum of squared residuals loss function, which the sum of squared residuals has way different units. It's in like the billions, whereas MAE is in like the tens of thousands. So this is going to make it so that our learning rates are not very good again. We're going to have to fiddle around with the learning rates. Look, our current loss is 1,000, million, billion, 4.8 trillion. It's a little bit bigger than 18,000. So both of these learning rates are going to need to go way down. But then this should converge exactly on the same values that that scikit-learn found. And it looks like we're still seeing divergence. So divergence tells me that my learning rates are too big, like way too big. Okay, so pound it with the zeros. Hey, that's a little bit better. It's going down. Loss is, both of these are going down, but not fast enough. Maybe I want them to go down a little bit faster. So maybe my learning rates are a little bit too small now. Let's back it off by a factor of 10 with each of these. Ooh, this might be the sweet spot. Oh, it's very close. We need either a little bit more epochs or we need a little bit faster learning rate. Still need a little bit bigger learning rate. Oh, this is the one. I can feel it. 107.14 and 18.555. Those are very close to, pardon my scroll, 117.13 and 108.569. So the intercept is still not quite converging. So let's up the learning rate for the intercept a hair more. Where were we? So much stuff in this notebook. Let's see if we get there. Bam, spot on. Okay, so in 500 epochs, we have now reached exactly the same slope and intercept that scikit-learn's linear regression function did. Even though it was calculating for it directly, we've done this guess and check, guess and check, guess and check 500 times iterative process to come to exactly the same conclusion. Now, you're probably like, oh, this is kind of ugly. Like, you know, is this really just guess and check? Is that what machine learning is? And the answer is yeah, a lot of it. But it's really, really fast guess and check. So that's good. But the reason why this is so important is because linear regression is a little bit unique, that we can calculate the slope, the very best slope and intercept directly. With neural networks that have hundreds, thousands of layers, millions, billions of parameters rather than just two, right? The math becomes impossible to have some derivative that can immediately calculate the minimum of the cost function. And in fact, our cost functions are not convex either. And so we may get lots of different solutions for our minimization problem. And it's not tractable. But this is actually very computationally efficient compared to trying to solve the world's biggest math problem that computers couldn't ever solve because the model is too big with way too many parameters, right? The direct calculation method becomes intractable as the number of parameters increases. But gradient descent is always pretty straightforward. It's much more computationally efficient. So when it comes to neural networks, this is how neural networks find their optimal parameters. This is how they choose, oh, should I bump the weights up or down? Well, is the gradient positive or is the gradient negative? Multiply the gradient by the learning rate and then bump those weights up or bump those weights down. There's a couple of other wrinkles in there with back propagation and activation functions and things, and stuff we'll talk about in the future once we get to neural networks. But I hope you can see how gradient descent can exploit the concept of having a loss function. If we have a loss function that can quantify the quality of our predictions, right? Where the height here is the quality of our predictions, and then we have all the other points are just combinations of parameters, right? If we can calculate how good our predictions are, given some random values for parameters, well, then we can use gradient descent. And that means we can use gradient descent in really any supervised learning situation. And we can help our models perform at their peak ability with this approach. So it's really powerful. It's really important. It's kind of the heart and soul of machine learning. And I hope being able to make these visualizations helped you wrap your head around a loss function. One of the things that was the most frustrating to me when I started to learn neural networks is people would just say, oh yeah, and then you minimize the loss function. I'd be like, what are you talking about? Loss function? Can somebody write down the equation for this loss function for me? Because like, where is it coming from? And it just was poorly explained in my opinion, which is probably why I'm overemphasizing all these things today. I hope it helps things sink in for you in the future. Do you have any questions for me about the basics of gradient descent and the things we've talked about tonight? In the future, once we get to neural networks, we'll do a gradient descent implementation again later on when we do some of that fun stuff. So you have that to look forward to. Next week, I promise we're going to finally include more than one x variable in our linear regression equation. We're going to move to multiple linear regression, and we're going to actually make some kick butt predictions. Not like amazing predictions, but pretty darn good predictions. You're going to be surprised how much bang we can get for our buck as we just start adding more x variables to our linear regression model. So we'll explore that, and then we'll get into regularization techniques where they're going to bring us right back to these loss functions, and you'll feel it come full circle. And I hope I'm really laying a good foundation with you for some of those future topics. So thank you for being here tonight. Thank you for your attendance, and please reach out to me if you have any questions that come up after we close the stream here. So thank you, everyone. Have a great night, and I'll see you back here Tuesday of next week at 8 p.m. Eastern Time. Thanks, everyone.